here we have something familiar. We have a power supply connected by 2 leads to a light bulb. We'd like to add something new, which is a connection to the computer so that we could measure the voltage with the computer also. If you look over here on the screen, it's got more or less the same voltages there. If I change the voltage, it changes too. So that doesn't seem so very helpful, but the nice thing about the computer is that you can make a graph of the voltage versus time. So now it's just measuring the constant voltage of 5.7 or so. But if I now increase it, it goes up. If I decrease it, it goes down. So do something dramatic, like plug it, and you can see it quickly keeping track of the changes in the voltage applied to the light bulb, and the light bulb turning off and on. Now, the reason we want to do this is not for the sake of the light bulb, but because of the capacitor on here. So we're going to wire this up slightly differently. I'm going to add the capacitor in parallel to the light bulb, and then reconnect our computer. Okay, so now I want to see what happens when I plug the light bulb in and when I disconnect it. And hopefully you can see that the light bulb turns on more slowly. And this is not just off or on. Let's disconnect the capacitor. Watch again. You can see that the voltage goes up and down very quickly, but then when we add the capacitor in, it takes some time for the voltage to reach the peak. And we would like to understand this better. Now, it gets a little bit tedious plugging and unplugging the power supply, so we're going to replace that with this other box over here, which does pretty much the same thing but automatically. So it's over there with the voltage going up and down right now. So we can check that by connecting this. So these are the outputs of the new power supply connected to the computer now, and you can see it's going up to 9.5 or so and down to 5.5 volts. Over and over again, and it doesn't get tired. So we could connect this back up to the light bulb, but I'm going to connect a slightly different circuit. I'm going to take this capacitor here and connect it to this resistor there. Okay, so the capacitor has 2 connections. I connect one directly over here to the resistor. Now I'm going to take my power supply and I'm going to connect one end to the resistor and the other end to the capacitor. So now we have our power supply connected through this circuit. It first goes to the resistor, again goes from the resistor over here to the capacitor, and then back to the power supply. Okay, and then we want to watch and see what happens. So right now, it's the same thing happening because the power supply is doing the same thing. But we also have the capacity to measure a second voltage with our computer. So I'm going to hook that up here. Hopefully, it's a little bit to the capacitor. Now, right now we don't have that turned on, so I'll go over here and turn on the voltage on the capacitor. I'm also going to turn on the voltage on the resistor, which you can get by the difference of those other two. Okay, so now we see, again, we have the voltage on the power supply going up and down like before, but you can see the same sort of gradual approach to that voltage that we saw when we had the capacitor and the light bulb together connected to the power supply. Okay, so the next thing we're going to do is we're going to stop this. And we're going to look at this. They're all sort of similar, but I'm just going to look at the resistor here. Okay. So this is the voltage on the resistor. I'm going to zoom in on this region here. Hopefully. And then I'm going to try to fit it. So I'm going to select a region of the data, and we'll do a fit. And we're going to try an exponential fit. Okay. And I don't know how clear it is in the video, but the fit is extraordinarily good. So again, if we zoom in on this region, you can just barely see this dotted line, the fit, because it fits so perfectly that it just blends in with the green line, which is the voltage on the resistor. Okay, so it's probably a better fit than any other experiment that we've done in class before, because it fits so perfectly. Electronics tend to be like that. They work very close to some kind of ideal situation. Okay, so next we'll try to figure out why this is behaving this way, both the voltage on the capacitor and the voltage on the resistor. So we'll be able to use Kirchhoff's laws and a bit of math to sort that out. We observed this circuit of a power supply, resistor, and capacitor connected in series. The power supply was switching between a low voltage and a high voltage. And we saw that the voltage on the capacitor sort of followed along, but it seemed to take time to reach the same voltage that the power supply was connected to. So we'd like to figure out why. And the main reason that the voltage on the capacitor doesn't change as abruptly as the voltage on the supply is that the charge is proportional to the voltage on the capacitor. And the amount of charge on the capacitor can't change instantaneously. Indeed, if you think about it, the current flowing into the capacitor is the rate at which the voltage changes. So if we think about what happens when the power supply changes from the low voltage to the high voltage, the current begins to flow into the capacitor and the voltage on the capacitor slowly increases. Now, Kirchhoff's laws will help us understand exactly how this procedure happens. So let's work that out. We have a circuit diagram here with the power supply, the resistor, and the capacitor in series. If we do Kirchhoff's voltage loop rule starting at the lower left corner, we find that we have the power supply voltage going from negative to positive, and then we have the resistor voltage but going from positive to negative, so we subtract that. And the same for the voltage on the capacitor. So we know that those must add up to 0. Now we use Ohm's law for the resistor. And we use our relationship here to replace the value of the current with the capacitance times the rate at which the voltage on the capacitor is changing. Now we can rewrite this slightly. Now we'd like to rewrite this in terms of this quantity here, Vc minus Vs. So let us make a new variable. V is Vc minus Vs. So the difference in voltage on the capacitor and the supply. Now if we take the rate of change of these things, since over the time that we're considering, the power supply is a constant, that rate of change is 0. So what we see is that the rate of change of this voltage difference is the rate of change of the voltage on the capacitor. So now using these substitutions, we can now say then that this is the rate of change of the difference, and this is just the difference. Now if we rewrite this just slightly, we see that the rate of change of that voltage is negative a constant times the voltage. This leads us to look for an answer in the form of an decaying exponential. We can check this by taking the derivative. And the derivative of an exponential is simple. It just gives back the exponential times the derivative of the exponent. But this is indeed negative 1 over RC times the voltage. So this is indeed the solution. Now we can return to our original variable. And we see this voltage difference is a decaying exponential. If we look at the initial time at t equals 0, we see that the constant A is just that initial difference, Vc at 0 minus Vs. So this gives us our final result. At an arbitrary time, the difference is the difference at t equals 0 times a decaying exponential.